Let me first start to introduce my collaborators and thank them a lot. First of all, the PhD student, Frederick Bippus, whose work whose work I will be mainly presenting. We have a larger collaboration in the framework of the correlated quantum materials and solid-solid quantum systems project, of which Kastenheld and Fake Assad are PIs. And there was also quite a lot of work of a project student, Christian Meyerhofer, who did some of the preliminary calculations, and the entanglement, quite a lot of entanglement knowledge and input comes from Gergerosch from Budapest. So let me now start presenting the actual talk. So I will not talk much about entanglement, but of course we are interested in correlated electron systems in this community, and the question is, what can we say about entanglement where we know that the correlation is strong? How do these things correlate with each other? And I am not an expert on entanglement, but since I've used for quite a long time now quantum field theory methods, I'm very happy to be able to link those two concepts, correlation functions and entanglement measures. And I will give a short introduction onto first how to obtain entanglement measures from 1 and 2 particle Green's functions that we obtain in many-body calculations. This is quite a technical work, and it took quite some time to figure it out, but I think it might actually be useful for many years in the future, how to actually link those two things. And then I will talk about the main part of the talk, about the results that we obtained for the 2D Hubbard model in the weak coupling limit for the entanglement measures that I will introduce at the beginning. This comes from a new preprint that appeared recently on CONMAT. Okay, so let me first start from the typical definition of entanglement, that if we take a two-side reduced density matrix and we cannot represent it as a separable object in that way, then we talk about quantum entanglement. And then there are measures of this entanglement based on the two-side reduced density matrix, for example, mutual information or negativity. And they have some good and bad sides. The problem is that actually none of them is measurable. There are easier ways to measure entanglement. For spin system, we can actually measure access in experiments 1 tangle or 2 tangles or 2 tangle. However, for fermionic objects, it's more difficult. For example, we can measure the susceptibility. As we saw from recent experiments in cold atoms, we can also measure higher order spin correlation functions. But from susceptibility alone, we can calculate something like quantum Fisher information that is defined here. And that already can give us also a measure of entanglement. But in this work, I would actually like to calculate entanglement measures from the two-side reduced density matrix. And these measures would be the mutual information and the negativity. So what is the two-side reduced density matrix? If we take the full density matrix of a system, what I will be talking about here specifically is a 2D Hubbard model on a square lattice. So let's take the lattice system, and we pick up 2 sides and trace out all other sides. Then we get the two-side reduced density matrix. From it, we can get the entanglement measures like mutual information. This is the Ij, or the fermionic negativity, and F. If we reduce our wishes only to this two-side reduced density matrix, we get a 16 by 16 matrix with 26 non-zero elements for the Hubbard model. And the rest is 0. So, okay, 26 non-zero elements. How to calculate them? I will get there later. First, let me introduce the mutual information and the negativity, the entanglement measures. So mutual information is something that is based on von Neumann entropy. So for us, maybe a little bit in correlated system, easier accessible, easier understandable, because we just take the entropy of von Neumann entropy of the full system and subtract the entropies of the individual components, whereas the rho I here is the one side reduced density matrix that we get by tracing out the other side. And of course, it has to be identical for I and j, since we look at translationally invariant system. The mutual information can be also non-zero for classically correlated states. And in this sense, it's only an upper bound on entanglement and actually on all correlation functions. And this is, for that reason, not a very good entanglement measure. However, there is a different, maybe a better one, which is called a negativity, which gives us sort of a lower bound. Because if negativity is actually positive, then we know that our state is not separable, that it is entangled. How do we get the negativity? So first we have to partially transpose our density matrix. The partial transpose basically consists of exchanging the basis vectors, and if we just transpose it partially, like transposing all the vectors that correspond only to one side, then if that transposition doesn't change the density matrix, if it's still a proper density matrix, then it will have positive eigenvalues, and it's fine. That means it might be separable. But however, if that partial transpose of the density matrix has negative eigenvalues, it means that for sure it's not separable. It is only a lower bound, because the opposite is not true. So if the negativity is zero, if there are no negative eigenvalues, it still might be that the matrix is not separable, but by chance the transpose of the density matrix still has only positive eigenvalues. And it's in that sense, it's a lower bound. However, the value of the negativity does not provide a strict lower bound. It's only that if it's not zero, then we have entanglement. This definition of negativity, however, is related to bosonic or spin systems. If we want to do fermions, we have to use something else, namely fermionic negativity. So fermionic negativity differs from the normal negativity in that instead of the partial transpose, we also do some time reversal operation, which basically gives us a sign change of the element if through the transposition we had to switch some fermionic operators. So it actually captures the fermionic character of the states, and for that reason, for fermions, we actually have to use this fermionic negativity. Another entanglement measure, well, actually not an entanglement measure, but a very similar quantity to an entanglement measure, the Renyi mutual information. As you see, although it's not a proper entanglement measure, because it also can be negative, it actually gives similar results to the mutual information. So this Renyi mutual information, because of the square of the density matrix, is relatively easy to compute with the quantum Monte Carlo. That's why I introduce it, because we will also like to compare some of our results to a benchmark, which is certainly not easy. And for that particular quantity, we could do that. So now I will talk about something extremely technical. But if you get lost, or if you don't follow this path, don't worry. The second part of my talk will be a bit more accessible. I will talk about the results. I, however, thought that the formalism of how to get density matrix, two-side reduced density matrix from Green's function is so interesting that I will present some important steps leading to that. So if we take the Hubbard model, we take only nearest neighbor hopping. We have the 16 by 16 matrix, but only, I think, 9 independent elements need to be calculated. Now, all of these elements are representable as equal time expectation values of either, in this case, 8 operators, so 8 creation annihilation operators. So 4 densities means 8 operators, or 6 operators. The off-diagonal elements have fewer operators, or even only 4. So if I take
Anna, just a quick question. What is
Yes.
the size of the system here?
What is the
Size of the system?
What is a system size independent? There's a
see.
16 by 16 matrix for any, so in thermodynamic limit it will also be, because I take out only 2 sides of the infinite system.
But you are assuming translation invariance then, right?
Yes, here I am assuming periodic boundary conditions, so in that sense also
And translation invariance, no?
Yes. So in fact, the calculations will be done with finite momentum discretization, but since they will be in the parquet gamma A formalism, they are in the thermodynamic limit.
I see. Because of course, at 0 temperature in the ground state, we may not have translation invariance, right? We may have charge density wave, spin
This
density.
is a finite temperature calculation.
Okay.
Actually, a
Thanks.
high temperature calculation in this
Okay,
sense.
thanks. That's what I wanted to understand.
Yes. So I do assume translational invariance. I do assume equivalence on the I and J sides, which simplifies my calculations so that I have fewer elements to calculate. I do not assume particle Hall symmetry, but other symmetries also, SU2 symmetry is assumed, which reduces the number of expectation values that I actually have to calculate. So the expectation values of 4 operators are like 2-particle Green's functions. They're, if I have a method that calculates 2-particle properties, I have them. However, the 8 operator correlators are not available. And in this case, we have to figure them out. We can do that because they're equal time. And if we use equation of motion, we actually can generate them. So from the commutator, there's an example of a 6 operator average that if we use the derivative of the annihilation operator, we can actually get equal time parts that have 3 operators. And by some smart reshuffling, we can actually get the 6-point correlation functions expressed as derivative of a 4-point correlation function plus some other elements. And in that way, we can actually express everything with maximum 4-point correlation functions. And these maximally, so we have a set of correlation functions that we have to calculate, 2-point and 4-point, and derivatives of them. And there's something like 15 contributions, depending a little bit on how you count them, 15 or 16. And each of them can be related to 1 and 2 particle Green's functions. And the 1 and 2 particle Green's functions we can obtain from, sorry. We can obtain from our many-body techniques that are based, for example, on DMFT, so on T gamma A or parquet equations or parquet T gamma A, but also other DMFT extensions that allow us for approximate evaluation of the 2-particle vertex. And then having that, we can just calculate the elements of the 2-side density, reduced density matrix. I give also an example how it looks in practice. So in practice, for example, this off-diagonal element is a 4-operator average. It can be rewritten into a Green's function. And actually, once again rewritten into a susceptibility. So this is an easy one. Susceptibility you can get from quite a lot of calculations. However, that element with one derivative is not anymore representable through susceptibility. It requires the knowledge of the three-point fermion boson vertex. That can be obtained from the two-particle vertex as well. So this is a more complicated expression, and the most complicated expressions, they contain the full vertex F, and you cannot avoid actually calculating 4-point functions in order to obtain these elements. And these C1 is an ubiquitous actually correlator that contributes to basically to most diagonal elements of the two-side density matrix. So it is a quite important one. Please note that all these final expressions, all these correlators, in the end have to be calculated at equal times. So I explicitly wrote here the time variables. At the end, they have to be taken to 0, imaginary time variables. So in the end, I have to sum over all frequencies. So the case here actually are multivectors, so the multi-indices, they denote momentum and frequency dependence. So in this case, I wrote explicitly this is the sum of the susceptibility. Here it's the sum over all momenta and all frequencies of the Green's functions and these 3-point or 4-point vertices. This is important to note because it means that we make quite a large error while calculating these correlators, because the asymptotics is not always trivial of these objects, and the cutoff error might be large. This is in practice how one does it. So we have a recipe. So however, we obtain the two-particle Green's function and the vertex. Once we have it, then we can compute the correlators and all the elements of the two-side reduced density matrix. And in the last step, we can calculate from rho ij entanglement measures. So the last step from 2 to 3 is relatively trivial. Step 2, once we have step 1, is actually quite computationally challenging. It's the sums over frequencies and momenta are actually numerically quite involving. And of course, the implementation of all these objects, of these elements and correlators with the correct signs and with the correct benchmark is a lot of work. And for that, I would like to thank a lot Frederick Pipus, who did a very good job at connecting the formalism with the actual data that were obtained from the parquet gamma A calculations. So we focus here on the Hubbard model, on the square lattice, and and only with nearest neighbor Kopik. And we will calculate the mutual information and fermionic negative as a function of distance. And also we benchmark our data with Renyi mutual information from lattice QMC. Again, this will be a bit technical what I say now, but since I don't want to talk about parquet equations now, I'll just very briefly for the record mention that in the parquet gamma A, I take only the fully reducible vertex from the DMFT, or in the next talk, you will learn that you don't have to actually extract the fully reducible vertex. You can change the formalism so that you can work with full vertex. The essence of the method stays the same. What is the ingredient is the fully irreducible vertex that comes from DMFT. The rest is actually obtained in a self-consistent manner. So we construct ladders through Bethe-Salpeter equations and plug these ladders into the F. So we have ladders in the particle-hole channel, ladders in particle-particle channel, and not independent from the pH channel, but in principle, we could also do an additional, Bethe-Salpeter equation for the particle-hole transversal channel. So that the F actually contains all kinds of ladders, and all kinds of Bethe-Salpeter equations are evaluated. We also update the Green's function through the Schwinger-Dyson equation, and the whole cycle is repeated in a round-robin manner, so that after convergence, we get the full vertex, and we get the self-energy out of the formalism. The actual implementations that I use is the multi-boson exchange implementation, in which we further decompose the vertices, but I have no time to talk about it in detail. The advantage is that some of the objects in that multi-boson implementation can be taken with much better asymptotics, and it allows for larger momentum grids. So with that formalism that you can ask me about, but I will not discuss, I get my results. That was the end of the technical part. So now I can talk about the way the calculations are done. So I have a converged DMFT calculation for a model, square lattice, nearest neighbor hopping, local interaction at some temperature. In this case, it was always almost always beta 5. The DMFT was done with the CT-Hype impurity solver in W2 Dynamics. And from some post-processing, I got the fully irreducible vertex. In the next step, I did the solution of the parquet equations and obtained the two-particle vertex, the self-energy, the susceptibilities, and also the screened interaction W and the 3-point fermion boson vertex somehow for free from that method. They can also be calculated from susceptibility and the F vertex if the method does not provide them directly. Now, the momentum resolution for the vertex was 16 by 16. For the Green's functions, it was 10 times larger. We did some fine graining. And with that setup, after convergence of the parquet equations, we produced the two-side density matrix. So let me now go to the actual results. We calculated the Rényi mutual information, the mutual information and fermionic negativity as a function of distance in the Manhattan sense. So 16 by 16, so that maybe the lower plots are more informative. So you can imagine the entire lattice. Here it is also the central side is our site I, and the two-side density matrix is between the site I in the center and some site J around it. So let us focus on the upper plots. They're actually quite similar. They all show that basically the nearest neighbor entanglement is the biggest, and it very rapidly drops to very low values with the distance. And here it's visible that for doping, in the doped case, the drop is not so dramatic. So in the doping, if we dope a little bit with holes at smaller electron fillings, we get larger values for the diagonal entanglement. And if we go now to the lower plots and look, for example, on the corresponding plot for u equal to 2, beta equal to 5, that would be this plot. So the largest value, it's the yellow one, that's the maximum, that's the nearest neighbor. And then the blue one would be the next nearest neighbor, and then there are some violet ones. So this, in the real space, we can say that this entanglement has some structure. It actually, whatever of the measures you take, it looks the same. Qualitatively, the picture is very much the same, whether we look at the fermionic negativity or mutual information or even the Rényi mutual information. Even though the actual values are different, the structure remains the same. So this is a busy plot. So let us look at the subplots one by one. Let us think a little bit why it actually has such structure. So okay, nearest neighbor is fine, but why we seem to have a maxima actually here, the violet color is stronger than the blue color. So it doesn't quite decay with distance. It has some oscillation. And it's actually universally present. So it's not only for this choice of parameters, but for half filling. So it depends, this pattern depends on filling. And now we focus on half filling. And in half filling, if we just go to u equal to 0, and in this case, we have perfect nesting in the square lattice, and the mutual information, that's the lower plot, can be calculated exactly. Sorry, this is here, it's the fermionic negativity, and here's mutual information, but the qualitative picture is exactly the same. In the pattern, we see that every on the checkerboard, every second side has 0 value. So the cross means that the mutual information is actually 0. And for that is the perfect nesting responsible. So, okay, so it sort of explains why we have so low values for some of the points here, but only like the difference between the points in the green circles here that are lower than the points in the red circles here. But it, however, does not explain why here along this line we have significantly lower values than we have along the diagonal and subdiagonal. And
Anna,
actually,
may I
yes.
ask you something?
Yes.
Do you observe Friedel oscillations?
Whoa, that
I mean,
is...
Wouldn't you expect to have that?
That would be in the charge. So this pattern corresponds more or less to the pattern of the magnetic susceptibility. We didn't look at. So
and when you observe this very rapid drop off for the half-filled case, I guess, and less
yes.
rapid when you have
Yes.
finite filling. And so
Yes.
is that an algebraic decay? I mean, I know it's numerical results, but have you tried to fit this?
Yes,
are there
I
reasons
cannot
to?
tell.
Yeah.
I cannot tell. The problem is that the values are not, this is not conclusive. It's if it's algebraic or exponential. So within the error bars, I can fit anything. So unfortunately, I cannot tell.
Are there
But
any?
it's a good question. I'll try to look at it more carefully.
And is there any analytic expectation that perhaps the fall off is exponential? I'm not quite sure.
So analytically, we have the value of the u equal to 0 that is creating this pattern. I don't think we have any analytic expectation for that. So
it's not so important at the moment. Thank you. Please go on.
But it's something that I didn't look from the perspective of the Friedel oscillations at. So we looked at the from the perspective of the spin susceptibility and these patterns. So in some sense,
you have if you don't want to take too much into the question time, you have about 5 minutes.
Yes, I think I'm finalizing anyway.
Right.
And so one thing is the difference between the points that are in the checkerboard pattern, and the other thing is the difference between the paths that are along X or Y direction and the diagonal paths. And I think this is not connected to Friedel oscillations because it shows a different pattern. But I did not look into it. So for the reason why the diagonal could be stronger than the straight line, one could say that if we're still in relatively weak coupling regime and we have only nearest neighbor hopping, then we have somehow different connectivity for these points. So points along this line are accessible only through one path, whereas for points, particularly for those 2 points that show slightly stronger values, we have 3 possible points of how to get from point I to J. So this could be the reason why we observe stronger values of entanglement for these points, and this is actually quite universal and more pronounced in lower temperature. So if I go to beta equal to 14, so beta T equal to 14, the unit here is T equal to 1, so the U value is given in units of T, and the beta in inverse T, inverse hopping. We see that these points are even stronger pronounced. Of course, it's an order of magnitude smaller than the yellow maximum. So the maximum, as we saw on previous plots, the nearest neighbor is significantly stronger. But nevertheless, these points seem to stick out. And this is also true if we go to the different value of the interaction. If we go to slightly stronger interaction of U equal to 3 for the same temperature and filling. But exactly, the pattern is different if I go out of half filling. And the same is in the exact solution for U equal to 0. The checkerboard pattern disappears, and we only have quite pronounced the difference between the diagonal entanglement and the straight lines, which corresponds to the nearest neighbor hopping behavior. So here it would be interesting to see if this hypothesis is correct. Then we would have a change if we included further neighbor hoppings in the structure of the entanglement here. That I could skip. Let me summarize. So the main result actually of the work here is that first of all, a theoretical result on the technical level, that whatever method we have that gives us output 1 and 2 particle Green's functions, that method can be used to calculate two-side reduced density matrix, and from that the entanglement measures. And the second message is more physical, that the entanglement structure is actually dependent on filling and not so obvious. So I would say I have expected a decay of entanglement, but not this kind of a pattern that we in the end found. The decay is very quick as a function of distance, but that's very likely related to the parameter regime that we are at. And because the temperature is high, the interaction is low. So it would be interesting to see other parameter regimes. So I don't know, pseudogap, criticality, great. Either with better parquet methods or with some simpler or computationally less demanding methods. What is maybe worth mentioning, that we did it for parquet dynamical vertex approximation, because there the vertex is really dependent on all momenta. And in that sense, we formally could show that all the summations over momenta and frequencies can be done, and that's that the approach is actually feasible when one actually takes into account asymptotics in quite a careful way. And with that, I would like to thank you a lot for listening. And I would encourage questions about anything in the talk. And once again, I would like to thank Frederick Pippus, who did quite a lot of good work on that topic.
Thank you very much, Anna. So I guess the talk is now open for questions.
I go to more interesting plots.
I see a question from Mario.
Can you hear me?
Yes.
Yes, hi Anna. I have a question actually, because would you expect that leather D gamma A, that in principle would be a bit cheaper, would perform as well as the parquet D gamma A in this case?
All to be checked, yes.
Okay.
I think it will perform better in the sense that it can reach more interesting parameter regimes. And if there are some of the correlations or that are some elements of the correlators will be in letter D gamma identically 0, and how big an influence it will have on the final results is very hard to assess from the current calculation. So one could think, if I now per hand put some elements to 0, what effect it will have on my plots. The answer will be inconclusive because it is a slightly different parameter regime that the letter D gamma A actually will best work at. So in the weak coupling, probably quite a lot of elements sum up in order to give that pattern. Whereas in the stronger coupling regime, where the magnetic fluctuations are very strong, it might be one part dominates and the other parts become small. So I don't know. So in one sense, this method will certainly work better because it can reach better parameters and more interesting parameter regimes. In the other sense, it will neglect some of the correlations.
Okay, thank you.
Okay, I see several hands now. So let me take the questions in order where they appear on my screen. So Martin Eckstein.
Anna, yeah, thanks for the nice talk. Maybe, I'm not sure whether this question is relevant, but there was some discussion on witnessing entanglement using this quantum Fisher information recently in the literature. Is there a connection to what you do? Or?
No, although we also have now a work on that,
Okay.
also with Frederick Bipus. So the quantum Fisher information basically only takes the magnetic susceptibility.
Mm-hmm.
So of course you can take the magnetic susceptibility from parquet D gamma A, but at the moment the parameter regimes that I can reach with my 16 by 16 grid is relatively limited. So for lower temperatures or higher interactions, the grid and the frequency ranges are not sufficient.
Mm-hmm.
But by the way, Anna, since we are talking about this Zoller-et-al. Formula for the quantum Fisher information, one question that has always puzzled me in that context is what's special about the spin channel? I mean, why wouldn't there be a similar formula for involving the charge susceptibility? Or
I guess so. It has to be. So
but
yes.
then it's a different quantity, right?
No. It would be quantum Fisher information connected with charge susceptibility. So
I think
you have to carefully choose the
Okay.
operators in the construction of the Fisher of the quantum Fisher information. But if you take other operators than spin, you can construct it from the charge as well.
But it's a different quantity, no? I mean, it's not the same numerical value.
Yes, it will not give you the same numerical value. It has also a more complicated question. So for the quantum for the quantum Fisher information, in that paper actually we took a particular momentum. So which momentum to take?
Yes.
So should it be the maximum of all correlators or should it be a special one? Yes, it's a valid question. Yeah.
Okay, I think next is Dieter.
Yes, thank you, Anna, for a remarkably clear talk in spite of the fact that this is really heavy machinery. You showed us this spatial structure in the entanglement. Now that is rather an abstract object. If you compare that with something that is easier to understand physically, spin-spin correlation function or density-density correlation function, is there any compatibility with that?
To some extent. So we compared a little bit with this with the susceptibility. I think I'm sharing screen, so I might actually be able to put the plot on susceptibility from the paper on the screen as well. It does not cover completely, but there is some relation. So let me just try to put it correctly on the screen. Oh no, it does, yes. Can you see the plots of the susceptibility? Yes, so that would be the magnetic susceptibility. It has this antiferromagnetic pattern, plus minus. This is a sign of the logarithm, and it also decays. And one can see that that plot, that left plot, would correspond to, I think, this plot. One can see that the pattern is different. So for the susceptibility, we do not, so we see that the local is the strongest and the nearest neighbors follows, but the pattern is slightly different. However, if we go off half filling, this is the n equal to 0.8. There are some similarities, although it's not exactly the same structure. So yeah, it's work to do. So I didn't plot all correlation functions. So especially for mutual information, it could correspond to a different correlation function that is connected to the concrete pattern. But yeah, for spin susceptibility, it doesn't seem to be one-to-one. But yeah.
Okay. Thank you.
And next, I think, is Jan van Delft.
Hi, Anna. Thanks for the nice talk. If I paid attention, you were using single-site DMFT.
Yes.
Do you have some intuition for how results might change if you would start with cluster DMFT as input into your computations?
For calculating the fully irreducible vertex?
Well, suppose you use cluster DMFT and then you put that into your D gamma A machinery. Would the results at the end change because you will have more local correlations in there, right?
Yes. So the approximation that we have local fully irreducible vertex certainly breaks down. It's not clear yet when exactly. And if I could calculate the fully irreducible vertex from cluster DMFT and then put it into the parquet D gamma A, then it probably would influence my results. I do not expect it to be the case for the U equal to 2, because for the U equal to 2,
yeah, okay.
quite up to quite low temperatures, the data actually fit with.
Yeah, no,
with,
fair enough.
with QMC
this question only makes sense in the limit of much stronger interactions.
Yes.
Yeah, okay. Thank you.
Okay, there is a question by Björn Spierski.
Okay, Anna, thanks for the nice talk. I have a question regarding your equation of motion trick. So you said you never need to compute the 6 or 8 point vertex because you can use this equation of motion. Does that what does it hinge on? Is it only valid for Hubbard-like models, or would it always work for more general models?
If you have a two-particle interaction, then you can generate all kinds of. So I could, if I make a first derivative, I get from 4 operators to 6 operators. With second derivative, I get to 8 operators. I could, in principle, continue with the two-particle interaction to generate higher order averages. However, I will only generate the ij. I can only do it for 2 sites. So the limitation is I cannot generate a 3-site density matrix, for example. So if I have ijk, then with the equation of motion trick, I cannot generate that kind of elements. And the crucial ingredient is also that the equation of motion gives me access only to equal time correlators. So I cannot generate 3-particle Green's function from a 2-particle Green's function without loss of information. So only in the limit of equal time, I can generate it. So that would be. However, if I have non-local interaction here, it will still work, I think. Yes, so it certainly works for all kinds of hoppings. It just looks a little bit different. But yes, so I don't know if you can extend it to other models in general. For spinel models, it should also work in some extent. Yeah.
Okay, we still have like 1 minute. So Henri Aloul has one question.
Well, okay, I don't know. It's not so important. The question is, apparently you don't reach the pseudo-gap regime in computation.
So for the u equal to 2, the pseudo-gap regime lies in for the parquet gamma A, it lies around 20. So with 9 form factors and quite good moment Q resolution, so really strong parameters, so very large objects, and around a month calculation, we were able to reach pseudo-gap. And in that calculation, yes, so I didn't store all vertices. So from that calculation, I cannot calculate all the correlators anymore. So I'm waiting for results from other calculations, either from development of the compression methods. That's one way of reaching lower temperatures and other values of interaction, or some smart method like the one that we will hear in the next talk by Fabian. So I'm sure one can calculate the two-side density matrix from the objects that Fabian has as output of his finite difference parquet.
Would you be able to get something which can be compared to the experimental observations, for instance, neutron scattering, the antiferromagnetic correlation length and things like that?
Yes, so the correlators, so I looked at the paper from the fermionic Hubbard model, all the spin correlators that were calculated. And the two-side correlators I can certainly obtain. I cannot, with that kind of method, obtain the three-side correlators. So that's limiting. So for that, the comparison would be possible for the two-side correlators. And if I could do the calculations in the pseudo-gap phase, I would have access to the two-side correlators.